All right, so we are going to finish up our 1.2 notes. I'm going to kind of start over just to make sure that we're all getting the same definitions as we go through, because these, as we introduce more vocab, understanding these basic definitions will help us understand definitions later, or the actual qualifications for some of our theorems and some of our definitions. So just to make sure we've all got it, a non-zero row or column in a matrix means that in that row or column there is at least one non-zero entry. That's important for when we want to write things in echelon forms, because one of the qualifications is that all of our non-zero rows are above any of our rows of all zeros. You could also rewrite that as all rows of entirely zeros, I'll abbreviate there, are at the bottom. So when we went through our kind of row reduction algorithm, which is not what we called it, but we just kind of intuitively solved in 1.1, we thought about what operations we might do. And so if we end up getting a row of all zeros, somewhere in the middle of our matrix, here is where, using that algorithm, we would want to use row switching to put that row at the bottom to be in echelon form. Another really important definition is what is a leading entry, and that is the leftmost non-zero entry. Notice that it doesn't have to be necessarily 1, because with our row operations we could always make it a 1 by dividing or scaling the row by a constant, but it is important that it is the leftmost non-zero entry. Okay, and later when we end up reducing our matrices more, some of these leading entries will turn into something called pivots, which is important. So a matrix, whether it's square or rectangular, is said to be in echelon form, and we will, sometimes it's called row echelon form. I prefer to call it echelon form because we already have something else that we're going to use, another RREF kind of format, so I will call these echelon forms. It has to have the three properties. I touched on one. Non-zero rows are above any rows of all zeros. So we've organized all the rows of zeros to the bottom. Each leading entry of a row is in a column to the right of the leading entry of the row above it. That seems like a complicated way to say that the leading entries make stair steps. Okay, think about the word echelon means something about a level, so each leading entry should be on a new level. Okay, so you could kind of even trace them as you went along. There are no more leading entries. Here are leading entries there. Okay, see how they make stair steps as you go down. And finally, all entries in the column below a leading entry are zeros. So we have already gone through and reduced so that everything underneath each leading entry is a 0. No other equation, because remember our rows are our equations, no other equations include a variable for that leading entry. So this is a couple of examples of echelon form that we looked at. Sorry, there you go. Of echelon form. Notice that the non-zero rows are at the bottom, and all leading entries kind of make stair steps, and it doesn't have to be exactly, the same. It may be that here in this column we don't have a leading entry, and that's fine because this is going to end up being a free variable for us. And these are some other, and we'll get to this later, basic variables, meaning these variables will be dependent on other free variables in this setup. Okay, if we want to take it further though, and echelon form is super nice, but it isn't able to explicitly tell us the solution to our system of equations. So it can prove whether or not there is a solution, and whether that solution is unique perhaps, but it can't explicitly give us the solution from the echelon form. And that's why we go to reduced, sorry guys, I'm really at a diagonal, reduced echelon form. So all the above conditions are hold, but then the leading entry now has to be 1. So we've scaled each leading entry to be 1 and its corresponding row. And each leading one is the only non-zero entry in its column. So the leading one is the only non-zero entry in the column. it doesn't necessarily mean that that leading one is the only non-zero entry in the whole row. And that's because we could have infinitely many solutions for some of these system of equations. But it has to be that for this entire column, above and below, this is the only time that this variable appears if it was in reduced echelon form. So here, it looks like x1, it has no leading entry, no pivot, as we'll get to later. So I know it might be a free variable in our equations. It could be something arbitrary. It's not dependent on anybody else. It could be anything. But x2, our second variable, we can write an explicit equation for x2. It's dependent upon other variables here, so x3, 6, 7, 10, and 11. X2 has to be written as a combination of those other variables, but there is no other variable that is dependent upon x2. Okay, see that x2 is not dependent upon x4 because x4 has its own equation here. Okay, that's what it means to be in reduced echelon form. From this form, we are able to then write the solutions to a system of equations. That could be, in this example, there are going to be infinite solutions because we have some free variables in which we could put anything in for those variables and get an equation that works. But it could also be that we could write a unique solution from reduced echelon form. Okay. On the back here, we have a couple of matrices that are in either row echelon form, reduced row echelon form, both, or neither. If something is in reduced row echelon form, then it is both row echelon and reduced row echelon. Just something to consider when we're thinking about both. I'm going to let you pause here and think about which format each of these matrices is in. So pause here, go ahead and check yourself with the filled notes before you come back. Make sure you try to justify why, or kind of identify what entry is messing it up, or what's kind of messing it up that makes it not in either row echelon or reduced row echelon. After you've done that, we're going to talk about the uniqueness of the reduced echelon form. Super important, and this is why we actually use reduced echelon form to write solutions for our system of equations. Each matrix is only row equivalent to, each matrix is row equivalent to one and only one reduced echelon matrix. That means that, let's say you and your friend are doing the same problem. If you do different row operations, maybe in different orders, regardless of how you end up getting to your reduced echelon matrix, you guys should end up getting to the exact same reduced echelon matrix. And that's because each matrix, each system of equations, has only one way to describe the solutions. Whether there is one unique solution, no solutions, or infinitely many solutions, there is one unique way to describe all of those cases, depending on what your system of equations is. In order to do that, and in order to kind of talk about more about how to get a reduced echelon form or a row reduced echelon form, there are three more definitions we need. And one of them is a pivot position. And that just means it's the actual location or position of the leading entry when your matrix is in echelon form. So it doesn't have to be in reduced echelon form, it just has to be in echelon form. Okay, so earlier, if you want to look back, pause here, the squares that were in our echelon form matrices are the pivot positions. Notice that it doesn't identify that a pivot position has to be a 1. It has to be non-zero though, because it is going to be a leading entry. A pivot itself is a non-zero number that is either used in a pivot position to create zeros underneath, or is changed into leading 1. So maybe a pivot could be something that's a 2, because maybe I have all even coefficients under that pivot position. That would be nice. Alternatively, we could change it into a 1 and then use that to kind of reduce everything beneath it. A pivot column is just something that has a pivot in it. So that is the number of pivot columns, and identifying a pivot column will also come in handy when we're talking about whether or not our system of equations has unique solutions or if there are not enough pivot columns, maybe it has infinitely many solutions. Being able to identify how many pivot columns there are becomes important to kind of proving the types of solutions we're going to get. So in this example, these are each pivots here, here, and here, and pivots, this column, and this column are our pivot columns. This is a really important note, so make sure you put a couple of stars by this. There is no more than one pivot in any row, and there is no more than one pivot in any column. Okay, there could only be one. And that also helps us prove things when we start talking about what the theoretical meaning of our matrices mean in a little bit. Something that we've already done in 1.1 is this row reduction algorithm. It's also in your book if you'd like to read through it. But there are 4 steps to the echelon form, and then the 5th step is to get reduced row echelon form. I really like to focus on, and again, this is why there's more than one way to get the right answer, but I really like to focus on choosing a leading entry in the top left corner, begin with the leftmost non-zero column. Okay, we call this a pivot column, and the pivot position is at the top. So let me start setting up this equation, or this matrix down here. So my coefficients for x1, going in order from top to bottom, are 1, -1, 0, 2. My coefficients for x2 are 1, 0, 1, -1. My coefficients for x3 are 2, 2, 2, and 1. And the augmented part of my matrix is -1, -3, -2, 1. Okay, so here, if I was following my row reduction algorithm, I begin with the leftmost non-zero column. Okay, this is the leftmost non-zero column. This is a pivot column. The pivot position is at the top. So we're going to use this as my initial pivot position. Okay, that is going to be the leading entry that I will then select a non-zero entry in the pivot column. Okay, non-zero entry, top left. It may be necessary to, if this 0 maybe had been up here at the top, maybe I'd have to row swap to get it to where I have a number as my pivot position. But I'm going to start with this one. We're good here. And now I will use row replacement operations, so adding or subtracting rows, using this row to get all zeros underneath it. Okay, so maybe my first operation, and I'm not going to do very many of these in the video because it takes a little bit, will be to do row 1 plus row 2 into row 2. Okay, so row 1 not changing. Oops, -1. Row 2 changing into 0, 1, I'm adding, so 4, adding, so -4. Okay, row 3 not changing, row 4 not changing. Okay, and you would continue to repeat the process until there are all zeros underneath that leading column. So I'd like you to continue on, pause here, see if you can do and complete the row reduction. It might take you a few minutes, and that's okay. We want to practice this by hand because I'm going to ask you to do a lot of it by hand. It's going to end up helping you in later classes, maybe when you can't use a calculator. I promise, teach you how to use a calculator and do row reduction in your calculator so that we can move on to more important concepts instead of just kind of our math operations. So go ahead and pause here and see if you can complete the row reduction and write out the system of equations. When you come back, it should be that your final matrix, after you've done a couple of row operations, appears so that there is a pivot in every column of the coefficient matrix, which would be the one, oops, that's supposed to be a 0, to the left of the augmented kind of line here, and then on the right side it should have 1, 0, -1, 0. Notice that there does not have to be a pivot in every row. In the kind of examples that you're going to do in class today or in the worksheet, sometimes when we have too many equations for the number of unknowns or the number of variables, we call that an overdetermined equation, meaning there's just more information than we need to actually get a solution or prove that there is a solution. And then I want to write out my solution as a system of equations, just like I started with. But if there is a unique solution, that ends up being just x1 equals 1. That's what our first row tells us. x2 equals 0. That's what our second row tells us. And x3 equals -1. Since there's a pivot in every column of the coefficient matrix, that means that there is a unique solution here. But there doesn't have to be a pivot in every row to prove that there is a unique solution. But this is our one unique solution. Okay? And if you need to show, you want to check your work, go ahead and check out the field notes to make sure that you are doing your row operations efficiently. Okay? So one other thing, so I'm not going to do another example with row operations, but a couple more definitions, and then we'll leave it to practice. Sorry, I'm really struggling with the paper. There we go. Okay, so again, I promise when we come back and we start 1.4, because that's where we're going to really start hitting up our inferences, I'll show you the difference in how to plug this in your calculator. You can feel free to play around with it if you like, but when we put a matrix into our calculator, using REF is going to be row echelon form or just echelon form. Remember, that's enough to prove something, but not enough to give us our explicit solutions. Row reduced echelon form is enough to prove and give us explicitly our solutions. So how do we write these solutions of linear systems? A couple more definitions that I've been using. A basic variable would be any variable that corresponds to a pivot column. So if there is a pivot in that column that corresponds to that variable, that is a basic variable. A free variable is any variable that does not have a pivot in that column. So here, our pivot columns are, and again, sorry computer science people, you're going to be super mad at me, but our pivot columns are column 1, so here's a pivot, 3, and 5. Okay, those are our columns. Again, I apologize, we are going to start with 1 though. That means our basic, and it helps because that's how we've labeled our variables, as x1, x2, x3, x4. I know we could probably label them as x0. Bear with me and the entire field of mathematics. I apologize. Okay, but our basic variables correspond to the columns in which there are pivots. So basic variables that will be given an explicit definition for their solution, are x1, x3, and x5. All of the other variables are free variables. So that means x2 is a free variable. There's no pivot in this column. And x4 is a free variable. And assuming that this, oh, no, they told us over here that this is, in fact, an augmented matrix. So this is the constants that are on the other side of our equations. This is not another column for another variable. So we have 3 basic variables, 2 free variables. So how do we end up, our final step in writing solutions would be to write them as we would call these parametric sets of equations. Okay, so one variable, x1, will be written in terms of other variables it is dependent on. So if I want to complete this previous example, which they moved from the augmented matrix to this system of equations over here, all we have to do is solve for the basic variables. So x1 will be equal to -6x2 minus 3x4. We want to put them in order, so I'll go x2 is free. We just say that so that we don't say arbitrary, we just say it's a free variable. X3 is 5 plus 8x4. You're welcome to put the variables of the constants in front, doesn't really matter. X4 is again free, and I ran out of room, but x5 equals 7. That one has an explicit definition, but we still consider this entire thing, okay, our parametric description of a solution set. And that's my abbreviation for solution there. Okay, so parametric description of a solution set. Again, each basic variable is parameterized in terms of the free variables. Okay. This is again also something familiar from BC Calculus. our general solution. Okay, and why can we say that the above this set here has infinitely many solutions? Since x2 and x3 are free variables, that means they could be assigned to any number we would like. And then the other x1, x3, and well, x5 has a particular number that it is equal to, but x1 and x3 would then be dependent upon what we plugged in for x2 and x4. So we will get an infinite number of solutions. Okay, again, a warning down here. Only the reduced echelon form can be used to solve a system. Echelon form is not enough. It's enough to tell you if there is a solution or not. It is not enough to tell you what the solution is. Okay, let's see. Thinking about one more thing. Okay. Our first kind of part of the theorem. Here we go. Existence and uniqueness theorem. Again, here's a summary for row reduction. I think you guys picked it up pretty well in class. It's pretty intuitive, but in case you like step-by-step instructions, there it is for you. So this is going to start kind of where we're thinking about theory and proofs. Okay, how can I know automatically if something is going to have a solution? So a linear system is consistent if and only if. That means that this is a bidirectional statement. If one is true, the other one will be true. So if it's consistent, I can say this. If the rightmost column of the augmented matrix is not a pivot column, okay, then I can say that it is consistent. So both directions work. So notice two things. One, it has to be that the rightmost column of the augmented matrix is not a pivot column, okay? And it has to be also meaning that when we reduce to just echelon form, not reduced row echelon form, but just echelon form, we don't have a row anywhere that says 0, blah, 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 0 equals b, where b is a non-zero constant. If b was 0, 0 equals 0. That makes sense. That's totally fine. But if b is non-zero, it can't be that all of our coefficients for our variables were 0, and I still got a number out. That doesn't make sense. Okay? A linear system is consistent. Then there are two options: a unique solution, no free variables; infinitely many solutions, at least one free variable. So that's important. Our definition of solutions is expanding to be able to say, I know that it is consistent if either of these are true, but if I look at my matrix and I see that there are no free variables, I know that there will be a unique solution. No free variables could also mean that there are a pivot in every column, okay, in the coefficient matrix. Notice I'm saying coefficient instead of augmented. So as long as there's a pivot in every column of the coefficient matrix, then there are no free variables. But if there are free variables, we know automatically that we will get infinitely many solutions. There will be no unique solution to this. Okay, so keep kind of trying to use these vocabulary words as you're working through the examples, and definitely writing out what does it mean. So if when I have a solution, like I did, I'm going to go back to example 3 here. Okay, once I have a solution like this, you could even practice by writing there is one unique solution, and it is this. Or if I wanted to practice using this one, you could say that there are infinitely many solutions described by these parametric equations. Okay? Using the vocabulary as much as possible will help you get used to kind of describing what's happening and how to know or how to prove that given a row-reduced matrix. So there are a lot of examples in the practice. The filled notes are completely posted, so I want you to go ahead and at least try some of them. Maybe try some of the smaller ones if you don't have a lot of time, you want to work on 1.3. But I definitely want you to, regardless of whether or not you do no row reductions or you move on, I want you to go ahead and answer these questions with a partner. Okay, try to answer some of these questions. Try to start testing your theoretical knowledge, your true-false. The filled notes have all of the answers and some explanations attached. And let me know if you have any questions. That's the end of 1.2.